Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Are interested in interactive graphics and rendering and acquiring very complex scenes, as well as marrying human perception with today's graphics.
Great. Thanks for the great introduction, Mike. Thanks so much for having us. So we've got this very pretentious title, and breaking the frame and interactive graphics. And of course, that's going to be relevant because we're going to talk about frameless rendering. And I sent this fairly pretentious abstract that tries to paint this very big visionary picture and hopefully intrigue you and motivate you. Hello. And I should mention, by the way, our students, Cliff Woolley and Abhinav Dayal, are major players, of course, in this research, but they're not here. So the motivation behind the abstract, just to briefly run through that argument again, is that there's a panel this year at SIGGRAPH, which is the major computer graphics conference, right? And the way they've assembled the panels for the last couple of years is you propose a topic, and then people can propose to be on, can sort of apply to be on that panel to talk about that topic. You don't get to kind of come in with your group and give a whole panel. They've tried to make it tried to make it a little bit more interesting than that. And so there was this topic proposed on the ultimate display. What would the ultimate display of the future be like? And there's actually Ben Stub and Abhinav who saw this go by and said, hey, we should apply to this, because they were looking for sort of display technologies, holographic displays, autostereoscopic displays, volumetric displays, and sort of out there display ideas. And we took a different tack. We started talking about this and said, well, look, whatever the technology, organic LED, projectors, LCOS, I don't know what it is, whatever the technology, it ought to have really high resolution, right? That's the one thing that most of today's displays don't have is decent resolution. If you sort of work through the math for a desktop monitor, say 18 inches away, you'd like something like 160 dpi or more in order to sort of support human visual acuity, to be able to draw things small enough that the human visual system couldn't notice them. And in fact, if you go through the argument and look at all of the various, let me just say 160 dpi, that sounds like a lot. I mean, typical displays today are around 100 dpi. That doesn't sound out of reach. But on the other hand, laser printers need to be a lot more than 160 dpi. That's mostly because of the halftoning issue, right? But there are hyperacuities in the human visual system that if you were to try to account for all of them, absolutely all of them, we figured by our math you need roughly 10,000 dpi, terapixel displays to do that. And there are people who can see the difference between 1,200 dpi printers and 600 dpi printers. You hold it at arm's length and you can tell the difference. So this is a real phenomenon. This is not completely absurd. But even if we back off of hyperacuity and say, okay, let's say 160, 200 dpi, but at the very least we'd like a very large display, right? We're interested, and this is part of the reason we're right here, is that people like Mike are working on very big displays. The very walls and desks in our offices should be displays, and they should be addressable to resolution comparable to today's printers. And furthermore, we'd like better temporal resolution than we have right now, right? Hardcore gamers often prefer to play on CRTs and to turn off double buffering, turn off sync to vertical refresh, and run the card absolutely as fast as they can to play at over 100 hertz. And the reason is that they play better. That amount of delay, even 15 milliseconds of delay can hurt task performance. And gamers know this, from playing Quake or whatever, and the human factors literature bears it out. You can actually harm human task performance by injecting as little as 15 milliseconds of delay. So to reduce that delay, run your frame rate way up. And if we do have autostereoscopic displays or holographic displays or some other exotic display technology, that's going to involve a lot more pixels, right? That's going to involve even higher resolution. There's a holographic display that's going to be pitched at this panel at SIGGRAPH that I think has 96 projectors all shining on the same screen with some sort. I don't know if it's lenticular or parallax or how they do it, but that's a lot of pixels. And there's the potential for different technologies are coming out that including the stuff that Mike is working on and thinking about that will do very that can make very small pixels. and a whole lot of them. Where are they all going to come from? So that's the motivation. Where will all the pixels come from? The thesis of sort of our work, sort of the motivational speech here is that recomputing and refreshing every pixel every time is a bad idea. For power and thermal reasons, if nothing else. If we're willing to settle for just a mere gigapixel display, a big wall addressable at visual acuity will get you a gigapixel display real fast, then you really shouldn't be trying to recompute and refresh all those pixels to say 200 hertz, which would be, we'd settle for that too. Okay, so the enabling technology is interactive ray tracing. So this is it's too bad Turner Whitted is not here, because I could throw his bad joke back at him. When I took intro computer graphics from Turner Whitted back in grad school, and he had this bad joke that he'd been telling ever since he invented ray tracing, which is basically ever since he invented ray tracing, people said, "Wow, those pictures look great. When can you do them interactively? This takes too long." And he'd say, "Well, just get a desert and get a field of, I think it was Vaxes at the time, get a field of Vaxes and put a red, green, and blue light bulb on each one, and have each machine trace a pixel and fly over that at 10,000 feet and look down, and you'll see a picture at interactive ray tracing." And that joke evolved over the years. By the time I took it, it was craze, and later on I think it just became PCs. But interactive ray tracing was an oxymoron, and then all of a sudden it just happened. The first what I would call a really true interactive ray tracer happened from the guys at Utah who sort of threw a supercomputer at it. This is Stephen Parker and Peter Shirley and folks demonstrated real honest-to-God interactive ray tracing. I'm going to use one of their videos as motivation in a second. But by the next year, Ingo Wald and Philip Sluselek and that whole group from Saarbrücken were working on doing this on regular PCs, or perhaps clusters of PCs, and we're getting nice results. Tim Purcell, Nathan Carr, John Hart. I mean, lots of really nice work from people on seeing if they can map this onto the GPU. They're building custom hardware now in Saarland. They've got a paper at SIGGRAPH that has an FPGA chip that does interactive ray tracing, and another paper coming out at SIGGRAPH that's really impressive is this. They're just using a regular CPU, and they've basically just optimized the heck out of this and come up with a couple of clever algorithmic improvements, and they're able to do a full screen, a 1 megapixel image at 30 frames a second of digital Michelangelo style models, super complex models. Yes.
Is that maybe what the IBM, Toshiba, Sony cell processor is supposed to do?
I think it's absolutely the cell. A lot of people think the cell processor is going to be a great ray tracing. It's not quite perfect. They made a couple architectural decisions that don't make it not the perfect ray tracing chip, but definitely that machine. There's no reason to think that you couldn't do cell. I mean, so Intel, to nobody's surprise, is thinking along lines that are not unlike cell, and ray tracing is going to be one of the killer apps. Post-raster graphics. So lots of people have done really nice work on how to get interactive ray tracing, and it's happened. We're not among those people. We're thinking along a slightly different line. What do you do with an interactive ray tracer? What are the reasons you want this instead of a standard polygon renderer, a standard feed-forward polygon renderer that uses rasterization? And of course, all the people who write papers on interactive ray tracing have answers to this. They tend to dwell on the sublinear complexity. So if you have a very complex scene, it's going to be faster to ray trace it than to rasterize. I think it was Jim Kajia who said that first. Because you've got this logarithmic acceleration structure that you can build. It's also a very nice flexible rendering paradigm. It's a very comfortable way to describe the way that light bounces around a scene, is to describe it in terms of the way that rays bounce. And so it's easy to write new primitives. It's easy to write shaders for flexible rendering. And I think the really good reasons, the best reasons of all, are that you can do really powerful lighting and shading techniques very naturally in ray tracing. And in rasterization, we have to work so hard to get even simple things like shadows. We have to really sort of bend over backwards and come up with and design our chips around algorithms for designing shadows. This is the Doom 3 NVIDIA NV40 story. And that stuff just comes really naturally in ray tracing, and let alone the more elaborate effects like indirect illumination, the fact that we can see the ceiling even though there's no light shining on it, directly on it. And that stuff's very hard to model in rasterization. Ray tracing provides a much more natural path. So we're not focusing on any of those either, although we definitely sort of think they're interesting. What we're focusing on is the fact that with interactive ray tracing and its ilk, you can vary the sampling rate across the image. You can decide, in polygon rasterization, you have to draw every polygon in the scene before you know that your image is correct. And it's not until you draw that last polygon that you know what, it could cover up the whole screen. So it's very hard to generate a partial image with polygon rasterization. Ray tracing goes the other direction, right? For every pixel, it tries to determine what color that pixel is. And so you can pick a spot on the image, anywhere on the image, and determine exactly what the color is there. So you can vary the sampling rate across the image. And from the very first work, from Turner's first paper, he talked about focusing the sampling around edge regions where there's some sort of high frequency to resolve. It's also a natural match, by the way, for perceptually driven algorithms. If you know where the user is looking, because you've got a good model of attention, you know what the task is, you can devote more computation to that spot and less elsewhere. And there's some folks at Bristol doing really powerful examples of this, that can show you, have you do a task where they sort of know where you're looking on the screen, and afterwards, they show you what you were looking at, and it's terrible everywhere except the one spot you were looking at. It looks awful, and you didn't notice at all. So ray tracing is a very nice methodology, a nice sort of modality for doing that. Beyond, not only can you vary sampling rate across space, you can vary the sampling rate across time. You can not only sample more densely in regions that are interesting, you can sample more often in regions that are interesting, and that's really powerful too. So this notion that we're going to vary the sampling rate across the image, and we're going to find the parts that are interesting, and we're going to sample them more densely and more often, is something that's it's quite easy to do with a ray tracing system, quite difficult to do with polygon rasterization. So, thinking broadly about what it is that we're doing, we are rethinking spatial and temporal strategies for interactive sampling and reconstruction. We're focusing on interactive here. A lot of this work has been thought of or sort of explored in the offline realm, where you've got an animation and people have done space-time ray tracing and explored that. We're focusing on the interactive case. And there's a whole bunch of related work, enough that you could fill the whole talk with it. So I'm going to focus on just a couple of key elements. The first one is frameless rendering. This was an idea that came out of UNC, published at SIGGRAPH '94, and it was kind of interesting because they sat up. This is my office mate. Sat up, gave a talk, and everybody kind of politely paid attention to the talk. And then they showed the video that they'd made, sort of simulating what this would look like. And the entire audience, this whole room goes, oh, it was really kind of striking how everybody kind of caught their collective breath when they finally saw what it looked like. So let me show you what frameless rendering is. This is framed rendering. It's a very complex scene. This is the Utah supercomputer ray tracer. And it's got all kinds of complexity, and so it takes a long time to generate every pixel. The frame rate is slow, chunk, chunk, chunk. If you don't wait until you've finished every pixel before you start putting pixels on the screen, so in other words, every time you compute a pixel, you immediately update it on the screen, and you compute those pixels with the latest input, in this case the latest mouse position, you get a very interesting effect. It's very low latency now. As soon as you start to move the mouse, some pixel somewhere on the image changes, and so you've got this very low latency, fast response kind of feeling. That's the good. The bad, of course, is that things tend to dissolve into clouds of sparkles. Wouldn't it be nice if instead of, and the reason, of course, is that as we move things, a lot of the pixels are stale, right? We're not updating everything all at once, and so some of the pixels represent older timestamps. They take a while to get updated, and so you see the good and the bad of frameless rendering here. We're actually we're getting lower latency response, but we tend to sort of dissolve into these patterns of noise, and they're kind of aesthetically pleasing in a way, but that doesn't help when you're trying to figure out that thing whooshing across the screen in a cloud of sparkles is a bunny or a cup or whatever. So we're going to build on frameless rendering. You can think of what we're doing as trying to sort of revive frameless rendering and build on it and make it work. Another technique that we use is a technique called sample reprojection, and a whole bunch of people have explored this in a whole bunch of contexts. These are just a few. The most sort of prototypical example is the render cache by Bruce Walter and colleagues at, for example, at Cornell. Basic idea of sample reprojection is when you trace a ray and it hits something, don't treat that as a 2D color on the screen. Treat that as a 3D color in space. And later on, when the camera moves somewhere else, don't throw away that color and start and compute a new one. Just leave it out there. Figure out where it would land on the screen according to this new camera position, and reuse it. So this is sample reprojection or sample reuse by reprojection. And it's not going to be perfect because colors most often colors change as you look at them, as you look at an object from different points of view. But it allows your samples to live a little bit longer than 1/60th of a second or whatever your frame time is. And so this is an example from the render cache where basically they were simulating a ray tracer that could compute 1/16th as many. They're running a ray tracer that can compute 1/16th as many pixels per frame as you would like for that frame. And if you just compute every 16th pixel, you get this kind of mush, right? You know, the camera is moving here, everything's kind of spread out, you get a big mush. If you only compute 1/16 as many pixels per frame and take the rest of them and do this reprojection step, you know, do the math to just figure out where that hit point, that ray hit point would have gone according to the new thing, you get a nice, crisp, clean image. Not without artifacts, but clearly much, much better than what you had before. And holodeck, tapestry, and shading cache, in a sense, are variations on this idea where they were stitching these samples. Instead of treating them as sort of a cloud of points, they were treating them as a 3D mesh or stitching them into a 3D mesh. In this case, they actually knew what the 3D geometry was and stitched it directly onto the 3D geometry. This is Tolle et al. From Cornell. And the final piece of related work that I'm going to talk about is just reconstruction from sparse samples. There's been what we're going to end up doing is we're going to do frameless rendering, and that means that we have sparse sampling. We don't have a lot of information spread around the image, and so in many places we don't have very current information. So we have to create an image from sparse, non-uniform data. And there's some nice work. There's been some nice work on this. This particular example is from Daniel Cohen-Orr and his group in Israel. And what you're looking at is an image in which most of the pixels have been removed, leaving data. Basically, most of the data is gone. The only pixels that are left are the ones that lie along these randomly chosen line segments. And you do their algorithm, which is effectively a sort of a hierarchical blur. And when it's all said and done, that's the image. And that's a pretty remarkable feat. That's not a lot of data to get a recognizable picture of Einstein. Whether that says something about their algorithm, and also probably says something about our visual system and its inability to do this automatically. But that's a pretty remarkable feat. So reconstruction from sparse samples is another piece of related work. We're not using an algorithm nearly this elaborate, although we'd like to look into it. But you see that this is an aspect of it. So a quick overview of what we're actually doing. We are doing spatio-temporally adaptive frameless sampling. So we're doing frameless sampling. We're going to just, instead of sampling until we create an image and then showing the user what the image that we've created, we're going to be continuously sampling in different spots on the screen, focusing that sampling on regions that are changing. And that change can be spatial change, meaning edges, high-frequency texture, that kind of thing in the image. It can also be temporal change. We don't really distinguish between these. We'll talk about that a little bit later. So we're going to prioritize sampling, sample more densely and more often in regions of change. And now what you have, if you think about what you've got with a frameless renderer, you no longer really have an image. You have this stream of samples, and they're distributed in space and in time. And so if you actually want to display that image on some sort of existing display hardware, you really need to do image reconstruction. And so we have this notion of a deep buffer. We don't have an image anymore. We don't have a frame buffer. We refer to it as a deep buffer. It's because it's got temporal depth. It spans time. So we buffer up recent samples across time and space, and then when it comes time to generate an image, which ideally should happen at least 60 times a second, on an LCD, for example, we reconstruct an image at the front edge of time by applying a filter kernel whose width varies across the image. And we'll talk about how it varies and in what way it should vary. But this filter kernel has extent in both space and time. So samples that are nearby have more weight than samples that are close. Samples that are more recent have more weight than samples that are old. And I'm about to hand it over to Ben. I'll just show you one quick preview of what this system does. Here is traditional frameless. It's got traditional in quotes because nobody actually really does this, but this is what the original frameless rendering would do. You sample evenly across the entire image, and you end up with this kind of mush of samples because the camera is moving here. On the other hand, if you use our system and do adaptive frameless rendering, you end up with a nice solid image. It's not perfect. I mean, you can see, for example, that there's very little data. I mean, look how few samples we have of this countertop, which has just come into view. So you're not going to get a perfect image out of the dozen or so samples that you have over there, but it does remarkably good. And it's doing that because in that region, it's giving a lot more weight to the recent samples than to the old ones that represent stale data. And now I will switch over to the video, and then Ben will take over for a while.
So do you keep multiple samples per pixel?
Yes, potentially. That's one of our advantages, is that over time, when things do go static, we can anti-alias. So I'll show you an example of that right here. Oh, so here's a quick comparison of, this is our toy example. Suppose that you're trying to generate an image, and you'd like to update it at 60 hertz, because that's what a monitor takes. And and assume you have enough, 1/10 as many samples as you need, that your sampling rate is 1/10 of that. You have a few choices traditionally. You could do high temporal detail. In other words, you could do the full temporal detail, create an image every 60 hertz, and do that at whatever resolution is necessary to reach that speed. Or you could do high spatial detail, where you go ahead and do the full resolution, the full image, and accept whatever frame rate that gives you, 6 hertz in this case. Or of course you could do something in between that, but we'll show these two as sort of extremes. And we'll also show frameless rendering, which is just this idea of taking that same number of samples per second and updating them in sort of random order, immediately updating them. And in the lower right-hand corner, you'll see our stuff, and we'll hopefully agree that it looks better. Okay, temporally detailed, terrible scintillating artifacts. However, it does respond immediately. You start to move the joystick or whatever, and the image responds. Spatially detailed. Okay, 1 sample per pixel, reasonably crisp image. Pretty bad aliasing, that's okay. But 6 hertz, right? If you tried to play a video game or a flight simulator, you would throw up. Traditional frameless, it responds quickly to motion, but during really rapid motion, things kind of dissolve into these clouds of sparkles. And I'm going to play that once more so that you can then, or a piece of it. Adaptive frameless, kind of the best of both worlds. When things move, we start to get a little blurry. When things get still, we start to refine an anti-alias. Yes?
You mentioned updating random pixels.
Mm-hmm.
I don't know about this context, but in the context of half-toning, random is much uglier than quasi-random. You want some kind of uniformity.
Fair enough. In fact, what traditional frameless does is it updates pixels in a randomized order, and they actually use some kind of clever subdivision of a Hilbert curve to achieve that. In our case, it's sort of guided randomness, so it is a little bit more pure random. And I think actually this is where we decided Ben would take over.
So I'm going to talk about some of the nuts and bolts of the system, especially focusing on the sampling. As we said, we do temporally adaptive sampling. So we have one component which is a sampler. It's framelessly sampling. Its sampling is guided toward, and we'll talk about how, areas where the image is changing either across space or across time. We treat color change across space and time more or less the same way. Just so you know, right now we're approximating change in color with the variation in movements. Then we have this component, a debuffer. This is where we collect all our samples. It buffers the samples across both space and time. In point of fact, we actually have 2 separate debuffers. One which serves as feedback for the sampler. The other which is the raw material for reconstruction. That reconstruction is both spatially and temporally adaptive as well. So we're doing filtering on this debuffer in a space-time volume and changing the support of the filters to reconstruct the image. The reconstruction bit is done mostly by Dave and his student Cliff down at University of Virginia, while the sampling bit is done primarily by me and my student Abhinav at Northwestern. We ship big streams, we call them, of samples back and forth to each other so that we can make pictures for each other. So sampling is both spatially and temporally adaptive. In order to achieve that, we use a spatial tiling on the debuffer. This is a technique that's been used in spatially adaptive retracing and rendering for a long time. The difference now is that these tiles actually have some temporal depth, so they enclose a space-time volume inside the debuffer. Then, in order to ensure that we can get good adaptivity, we try to maintain roughly equal color change in each tile. So that means that where there are edges, where things are changing, the tiles will be very small. And where things are not changing, the tiles get quite large. The way we do this is by splitting and merging tiles in a KD tree. so that where if things are not changing, if there's not an edge or not motion in a certain region of the image, we might merge two tiles together. And then at the same time, if things are changing quite quickly, we might split some tiles. And then in order to achieve that activity, all we have to do now that we have this collection of variously sized tiles, roughly equal color variation in them, is randomly select one. And then randomly select a location within the tile and sample that location. So this turns out to be a very closed-loop feedback process. Unfortunately, it's a very complex closed-loop system, control system. But we can do some optimizations. I won't go into details, but we can use a PD controller that responds to where not only the color is changing, but where the color change is changing. And we can also do some gain control so that we're not too adaptive, for example, and we don't try to make poorly informed decisions when the signal or the image is changing quite rapidly, a little faster than we might keep up with the current level of activity. So here is an example showing how our tiling is working. What's going on here is that the viewpoint is actually moving to the right. And so you can see here small tiles over spatial edges so that we're getting some spatial additivity. And I think most interestingly here, this is an area where the edge of the table is including the floor behind it. You get a lot of small tiles over that region as well, in addition to the spatial additivity. So we're sending all our samples where we need them to go.
So tiles are aged together? Is that the...
Aged?
I mean,
I'm not sure what you're...
Is it treated as a sample over time? I mean,
the tile is actually just a region that's used to guide sampling. So we're compiling statistics over the tiles, over the samples in the tiles, and getting one measure of color variation over space-time per tile. In fact, I think I might be previewing things a little bit. The variation, the samples are actually weighted so that new ones count more than old ones with this visual function. In addition to computing all this variation and finding colors at certain locations in the image, we also compute color gradients. The gradients are used for our gain controlling how adaptive things are. But more importantly, they're used in Reconstruction to shape the filters. And so here, we're just showing you the viewpoint is static. We're showing you the most recent examples, no Reconstruction here. And the car is moving across the scene, the toy car. And what we're doing here is mapping gradients to color. So blue is a temporal change in color, and green and red are spatial change. And we're sending that kind of information on a per tile basis to the Reconstructor so that it can make Reconstruction adaptive. As I said, we use a KD tree. The mechanism we use to manage merging and splitting is taken right out of the level of detail literature, where in that case they're generally merging and splitting polygons. In our case, we're just merging and splitting these spatial tiles. We use two priority queues to decide which tile gets split next, which tile to merge next. When we sample, as I say, it's important that we send gradients to the Reconstructor. So we do this, we find gradients by shooting clusters, in this case crosshairs of rays. The idea is that, first of all, shooting clusters turns out to be, because of today's graphics architectures and CPU architectures, shooting cluster grades is almost free because we're just going to hit cache most of the time with these extra nearby samples. But the real motivation for doing this is that it is the right way to measure gradients. If we don't do it this way, we might conflate spatial change with temporal change. For example, if we just compared the sample we're making now to the last sample we made nearby, that would not only be nearby in space, that would be nearby in time. So we wouldn't know what sort of gradients we're getting. And as I said, gradients and variance age more quickly as they get older. They count less as they get older in the gradients and the variation.
Oh, I was going to pop up here since this is sort of the part that we. This is the part that we do at UVA, where we actually write the code. So, as I've said, the stream of samples that's coming now is no longer an image; it's an incredibly non-uniform distribution. In fact, at the end, we'll show a video, another part of that video that shows you exactly sort of how much the sampler is succeeding at focusing on the regions of spatial and temporal change. And so you have very dense sampling there, and only occasional sampling elsewhere. But we still need to make an image out of this, despite the fact that the samples we have, have different ages, and they're very non-uniform in space and time. So we do a filter from the deep buffer to the display. Just like standard image reconstruction, image filtering, we apply a filter at every kernel. It's got some fall off, Gaussian or otherwise. The difference is that now we're filtering in space and time. So this is a volume. You can think of this filter as having a volume. That volume is determined by sampling density. And so what we've chosen to do is choose basically the same. We've chosen to choose our volume according to the local sampling density, the same way that we would choose it if this were uniform. So just sort of thinking about the Nyquist limit and how broad you would want your filter to be if this were uniform. If this were uniform sampling, we know the local sampling density. Let's shape our filter according to, or size our filter according to that local sampling rate. But then we're going to perturb that size. We're going to achieve that size with an infinite number of filter shapes, right? We're going to choose x, y, and time widths as determined by the color gradients. And the motivation is this. In regions of the stream, regions of the scene where things aren't changing very much, the old samples are useful. They should have nearly as much weight as the new samples. And we can, because we can accumulate them and eventually have multiple samples per pixel and use that to anti-alias the image. This means basically that we have temporally broad, spatially narrow filters, right? Sample weight does not fall off rapidly with time, but on the other hand, you're trying to sharpen the image, and so you don't want samples from way, way over there to contribute much to this pixel. On the other hand, where things are changing rapidly, the new samples are useful, and the old samples are stale, they're harmful, they have bad old data. And so you want to emphasize those new samples over the old samples, even if the resulting image is less sharp or downright blurry. Spatial width, in this case, should dominate, because you do want new samples to be able to influence a radius of many pixels, of several pixels. And temporal, so you have a spatially broad, temporally narrow filter. The temporal fall-off should be rapid. And just as sort of an example of this is a scene from that same stream. The camera is flying across to the right, and then it stops. It basically stops. And so you can see this is a much blurrier image. This is after a few milliseconds, maybe 16 milliseconds or so, maybe a little bit more than that. This is during rapid motion. So this is definitely blurrier than this. Here we've started to sharpen the image. Compare this to the same exact moments at the same exact sampling rates with traditional Frameless, where we're just shooting samples in sort of this randomly distributed pattern across the whole image, and we're updating those pixels immediately. The trouble with traditional Frameless, as I've mentioned several times, is that it basically this lack of reconstruction, or this very simplistic reconstruction, causes these things to completely break apart. And so it, clearly the image on the left, I think you would agree, looks better. Even though it's a little blurry here, it looks solid. You can tell what you're looking at. You can see the cups. Here, the cups have dissolved. On the other hand, the image on the right, it looks nice and crisp here, but it's certainly got pretty bad aliasing problems. Whereas here, we're starting to actually accumulate multiple samples per pixel, and we're starting to anti-alias. And we're not doing a perfect job. Filter design is kind of an open question. We haven't figured out exactly the right way to design these filters. But I hope you'll agree that looks better, at least more anti-aliased than this.
Isn't it kind of an unfair comparison because there's so much trash high-frequency information in that one?
Oh, I'm comparing this one over here now. I'm comparing. Oh.
That's what I mean. Like.
Well, but remember, this is a limited sampling rate. I mean, what would you do differently?
That one on the left?
Yeah.
To make it blurry?
Yeah.
You want a low-pass filter, the one on the left.
Even if you did that, I would probably agree that your results are better. It's just when I look at that, all I see is high frequency.
Well, I mean, it's one sample per pixel, which is, if nothing else, is typical. You would probably, you would like to do better, even.
You're launching artificial high frequency. that we perceive.
Yeah, you're
as
injecting
bad.
all sorts of noise into it. I mean, it
Fair enough.
easily
Fair enough.
take care of some level.
Fair enough. True. No, that's true. That's true. That's probably a slightly unfair comparison. It's kind of hard to do fair comparisons of these techniques, actually. We've struggled with that in writing papers. The filter design is a bit of an open question. You know, we've implemented a bunch. You know, the ones that you would expect to be kind of naive, in fact, don't do great. Filter design temporally is kind of an interesting question. Imagine a red pixel and a blue pixel arrive one shortly after the other one. A red sample and a blue sample arrive at the same pixel, one shortly after the other one. So the red sample arrives, the pixel's red. A little bit later, blue sample arrives, the pixel, you know, there's still, say there's a Gaussian fall off of weight, which is probably the first thing you would try, right? As long as the red pixel is still fairly recent, you're going to get kind of a purple, or the red sample is still recent, you're going to get a purple pixel. And then time passes, these two age at the same rate. The red one kind of falls off falls over the hump of the Gaussian, and your pixel starts to turn blue, and then the blue one falls off, and your pixel turns purple again. They start to have nearly equal weight again. So if you want to prevent this differential aging phenomena, which we've decided actually isn't all that important, but we thought might be, you would use an inverse exponential. Not great bandpass properties, but at least prevents this. That's how you shape a filter to prevent this. In practice, we use Gaussian a lot. We experimented with the Mitchell filter, which is sort of a classic non-uniform sampling filter. But that doesn't work so well, and it has mostly has to do with the fact that we've got a GPU implementation of the Reconstructor. We're doing the Reconstructor on the GPU because it's fast. We can achieve 20 frames a second or so on the sort of the low resolutions that we're using as examples. But to do that, we're having to do all kinds of crazy things, like use the 16-bit floating point blending and so forth. And basically, we think the negative lobes in the Mitchell filter don't marry well with the low precision that 16-bit floating point gives us. The good news is that we can do reprojection. We talked about sample reprojection at the beginning, reusing samples and sort of moving them to where that comes for free in the GPU because you just refer to these samples as a vertex array, and the GPU is very good at dealing with vertex arrays. So it's basically just not even reprojection, it's projection. You store all your 3D hit points, and you just say render. And it becomes a splatting process where the GPU renders all of these and maps each to a point sprite and runs some very elaborate floating point blending and fragment programs to do the blend. So I'll sit down and let Ben carry the talk.
So reprojection. Reprojection turns out to be really important and it's very useful in our system. So if we just look at regular image using traditional frameless reconstruction to put up the frontmost sample, the most recent sample at each location, it looks like this. But if you add reprojection of those samples, if you know something about the 3D location of the samples and relocate them according to the current view, then you get a much more coherent image. I should point out here that in addition to there being some car motion in this case, there's some viewpoint motion. So there's still there are still a few artifacts here. You can see some spottiness in the reflection in particular on the floor. And the car here is actually got some blurriness because some of the older samples in the car had vectors of motion that were moving straight across the scene. But more recently, the car is turned towards the viewer. And so you get this kind of splitting ghost-to-car effect going on. But if we add reprojection, add adaptive frameless rendering with reprojection, then you can get rid of a lot of those artifacts. In particular, the old samples that broke up the reflection here, a lot of them go away. The newer ones are emphasized, and that ghost car completely goes away because all those samples that we were reprojecting are old. So with both together, we still get a big win with the adaptive reconstruction as well as reprojection. So reprojection happens, is especially important when we're, the way we do this, we track camera motion, we track the sample's location and their velocity. We have some trouble sometimes when we're undersampling areas near moving edges, but we make up for that by sampling more often. And so what we do in that case is we sense the change in those regions, sample more often, and the reconstructor uses broader filters. In this case, you can see we're getting much more dense sampling. This is a density image showing where sample density is particularly high. And that's how we address that disocclusion problem, which is something that is always a problem when you're doing reprojection. If you don't do something like this, you don't have any samples at all, you'll open up gaps at disocclusions, and you'll get at occlusions competition, where you have occluded and not and occluding samples in competition with one another. We can solve that problem with better sampling and better reconstruction. So the sampler uses reconstruction quite a lot. Uses reprojection quite a lot to guide sampling. It keeps the sampler informed not only where things are, edges are, and motion is currently, but also where, in particular, occlusions and disocclusions are happening. The mechanism that to accomplish it is that after we make our spatial crosshair samples in the sampler, we schedule another visit a fixed time later, come back to sample how the color might have changed at that location since we first made that crosshair, and then we use that to form our temporal gradients. We have experimented quite a lot, in fact, with doing more reprojections to get better detection of occlusion and disocclusion. And this really is the major issue in using reprojection. We currently are sort of, instead of just revisiting once, we schedule some extra reprojections to gain sensitivity to occlusions and disocclusions. But there's a trade-off there, because the more reprojections we do, the slower our sample becomes. And in the Reconstructor, things are quite different. All we need to do in that case is we load the samples into the GPU as a vertex array, and then their reprojection simply becomes just rendering the vertex array according to the new viewpoint. And so we actually reproject all the samples in the temporal buffer that is used by the Reconstructor. And this gives us really, this is very coherent and very hardware friendly. Now there is an issue here because this sort of combined GPU software implementation has introduced a somewhat artificial split of the temporal of the deep buffer into two organizations. In any kind of production system, we probably want to figure out some way of combining those. In fact, in our original software implementation, we didn't use the GPU in that case. We actually were doing reprojection directly off the deep buffer, the same deep buffer. So, video results.
I left this in the oh yeah, I left this in the wrong place for you. Oops. So this first part is the error imagery. Okay. And then let's skip around.
So combining both sampling and reconstruction with reprojection, how well are we doing? Here we're going to look at some error images. We're just differencing imagery. The imagery produced with the same techniques you saw before with sort of some hypothetical renderer that could render everything in 0 time with anti-halos. So with the temporally detailed system, you see a lot of error around, even when seeing static, around hyperplastic edges. And with things, let me back up. And even when things are in motion, there's some error were introduced because of lag. Here, the lag problem is in the detailed scene where we render every pixel, we sample every pixel. Lag is a much more serious problem. Whenever there's motion, you see a lot of error. In the traditional frameless renderer, you see error during motion, exactly focused on those sort of scintillating temporal artifacts. Whereas with our approach, things tend to stay black. And you get not much error.
So this is the part I think I would skip for lack of time. There you go.
So now I'm going to show you a glimpse of the internals of the system, just to give you an idea of how few samples we're making do with. This is the samples available within the last 16 milliseconds. Now I think we've jumped to 33 milliseconds. And then finally, what is that, 60 milliseconds?
Yeah, I think that's 4 frames worth of samples if you were doing frames.
You can see quite easily how the sampler is focusing those samples on images. Let's look at that one more time. Now remember, we in addition to having these last 16 milliseconds of samples to make the image, we also have the temporal buffer behind it, so we have the older samples. So in each case where we double the number of samples here, we're giving you a sort of more accurate indication of what's available to us. And you can see again how we're focusing sampling where there's occlusion, spatial edges, and motion. Here's another view. Here we're showing you the current gradients in the image on a per tile basis. Again, the sample density in the scene. Here's the current tiling that we're using, dynamically being adjusted, and here's the output image.
I believe those, by the way, are 60 hertz imagery, slowed down to 30 hertz to sort of show it a little better.
So our current system is largely simulation. Even so, we use just to push things as much as we can, and for ease in development, we make things as fast as we can. We use OpenRT from the Zarberg and Ray Tracing group to do our sampling. It gives us about 25,000 samples a second. For each of those samples, we trace roughly 10 rays or so, perhaps a bit more. That's not the best that OpenRT can do, but remember we're doing things in a very incoherent way. We're using a lower level per ray API, so we can take advantage of the spatial coherence and memory coherence that OpenRT otherwise uses in its range of information. We usually simulate at about 400,000 samples per second, and we produce most of our results, our images. They're 256 pixels squared, so we're sampling about a tenth of the rate that we would use to sample every, that would be needed to sample every pixel once. That's 60 hertz. The Reconstructor, as we said, uses a vertex array, so the samples turn into GL points, which are splatted onto the screen, and then with some very cutting-edge vertex and fragment shaders, we do the filtering on those slats, and each of the pixels in those slats. One small issue with that is that we have to decide how big to make those slats. Now, you could conceptually make the splat cover the whole screen every time, but that would be far too much overdraw, so we use a small feedback mechanism to change the splat sizes to make sure that we try to make sure that we have just as many pixels as we need to do our filtering without getting too many. And in this Reconstructor on the GPU implementation, we can do the reconstruction on our 256 squared images at 20 hertz rates.
Well, we can go faster than that to keep fewer samples.
Right.
But that's per million samples.
I'm curious about how well OpenRT's caching and acceleration techniques, the ones that you had to put aside to do this.
Let me address that. I'm going to talk.
Okay.
I'm going to wrap up the discussion of coherence. Let me come back to that.
To evaluate this, in addition to just looking at things, which is always really important, as I said, we create an ideal rendering. This rendering produces a hypothetical render that could produce sample every pixel or wherever in the scene as often as you want in 0 time. And so we simulate that offline, make enough samples to do aliasing, and use those as our standards of comparison. We then compare the images we generate against that standard. We have to be careful about how we line these things up temporally to account for frame locking and all that kind of stuff. And we compare these to some of the things you've seen in the video. We compare them to sampling every pixel once, no matter what the frame rate, making sure we sample 60 times per second, or sampling or using a standard frameless renderer.
And
so here's what the results look like. Do you have a question, Jeff?
No, wait.
Here's what the results look like. We're using Richmond squared comparisons. It's a good indication of a good rough indication of how well we're doing. We did, by the way, look at using other perceptual metrics, but most of the metrics out there, and we did well in those metrics, but we were unsatisfied with the metric itself because most of the metrics out there are really about telling you whether or not one can see the difference, not how different are they. So, in fact, I was speaking to Scott Daly recently, and he said that's a big area of work for him, super threshold perceptual error. Anyway, the big black curve here represents how much error our adaptive frameless renderer has compared to those ideal rendering. Whereas all these other measures, all these other curves refer to the other rendering techniques that I mentioned before. There are some particularly interesting ones. Here, this thick gray line shows adaptive frameless rendering without reprojection, and you get a sense of how important reprojection is to the system. Fairly important, but we still do quite well. Let's look at this green line here. And this is, I think, a real punchline. This green line actually represents a 60 Hz renderer that uses 10 times the sampling rate to sample once at every pixel. And we're at least competitive with that, and in fact, often better whenever the scene goes still or any aliasing uses less error. Now here we're looking at, well, I should say, by the way, that previous graph showed the kitchen scene that we showed so often where things are moving around on the table.
So what was the pulsing pattern? Was that because it was looping or something?
What here?
No, this previous slide.
This was periods of viewpoint motion. Each of these pulses represented.
That's exactly the video you saw.
Okay.
Moving, stop, moving, stop.
Okay, so those repeat.
Well, it's not repetitive, but it's the video you saw.
Similar
for a little bit,
motion.
and we slow down because we're trying to show off those static and dynamic scenes.
Okay.
That's what that is.
So the motion is
The motion is somewhat periodic by accident.
Okay.
So here's the scene where there's no viewpoint motion, so things are in general much more static. The only motion in the scene is in the toy car moving across at first field of view and then turning forward to the point of viewer. And here again you see we're always showing less error than images. This sawtooth pattern here is particularly interesting. This is the sample once per pixel no matter what the frame rate approach. And you can see the cost of double buffering here, illustrated graphically. Because as the frame display ages, it becomes a worse and worse approximation.
Yes, so I'm curious how that looks in real life, because I would think that since the display is being, I mean, the CRT anyway, since the display is being updated, you wouldn't want an interlacing effect, would you? You want to render you don't want to render as many pixels at one point in time using frameless rendering until you knew that the display was retracing, at which point then you want advanced time. Is that right? I mean,
So are you asking about frame locking?
Maybe I am. I'm sorry. This is not my area, so I can't even speak coherently in it.
That's okay. This is so this is the effect of double buffering, and we were using frame locking in this case. So that made sure that you didn't swap the buffer until you were also refreshing the screen on the display.
Okay.
In this case, it took longer. It took several refresh times. I don't know exactly how many, but several refresh times.
10. I see.
10. Yeah. 10 refresh times to finish the frame in the back buffer and swap it in. Okay, so overall, then we've shown you a technique that is better than traditional frameless rendering. So in some sense, it's frameless rendering done right. But more importantly, I think it's better than traditional framed rendering, especially even at low sampling rates. But more interestingly, we get lower error even when we get better images even with 10 times the sampling rate. Now, we should caveat this by saying, again, this is all simulated. We think it could be done a lot faster, but our goal wasn't necessarily to produce an interactive rendering system now. Really, our goal is directed toward very large display systems or bandwidth-limited display systems, where you're trying to do interactive rendering. In that case, this kind of 10 times win becomes a very important result.
Yeah, this is my sort of wrap up. Sorry we're running a little late. That's probably an artifact of trying to switch speakers on you. If you've done anything in fast ray tracing, I don't know if anybody in this room has, all of the fast ray tracers out there, and there's like 4 or 5 now, make a big deal of spatial coherence, taking advantage of spatial coherence in order to get memory locality. And frameless rendering in general implicitly gives up some of that coherence, right? You sample here and here and here and here, and your cache is just gone to hell because you're loading in completely different chunks of geometry every time you take a sample. Now, we're not quite that naive, in fact, as original frameless sampling. Remember, for one thing, that every time we sample in a region, we actually sample several times in a region because we want to gather these gradients. We're shooting these little crosshairs. And furthermore, we have this tiled structure. There's nothing that says we only have to sample once per tile. We have this tile structure, and those tiles are likely to fit in cache, and so we can take advantage of that in a temporally multiplexed or in a parallel distributed architecture. So we think this isn't the end of the world. We might need to go even further and really think about not try to get true random access to these tiles, but go ahead and organize the random samples around exactly what's in memory. We have a couple ideas on that. But implicitly, we're gaining a kind of temporal coherence that regular rendering doesn't take advantage of. Normal rendering, you generate every pixel and you throw them all away and do it all again. And part of our sort of argument is that you shouldn't do that. You don't need to resample everywhere, every frame. And so we get, arguably 10x fewer pixels, fewer samples. And so if we could design a parallel architecture around this temporal coherence, we think that might be a big win. If we can address these spatial coherence concerns a little bit and exploit this temporal coherence, we think there's a big win there. Take this to the extreme, and this is the kind of stuff we've been talking about with Mike Sinclair this whole visit. What if the reconstruction process happened in the display itself, so that what came over the wire was not a stream of images, one after another, full resolution, but a stream of samples? The analogy I always like to use, and it's visual, it's sort of visual, if nothing else, is to think of the display as a systolic array of pixels, and you're throwing samples at it like we're throwing darts. And they diffuse out some color, they compete with other samples that have arrived nearby, and the reconstruction happens truly on the display, possibly even at logic behind every pixel. If you had something like this, then this would really make a big difference in terms of parallel graphics. There's a whole bunch of parallel graphics frameworks, sort first, sort middle, sort last, variations on these. This sort of taxonomy of parallel graphics. And parallel graphics is a classically hard problem in many ways. This lets us get truly asynchronous parallel graphics. If you had multiple samplers all sampling as fast as they could, with whatever they had in cache, you could have this stream of samples coming over the bus or over the wire, and have all the reconstruct up on your display. That actually is a really powerful idea because we don't have this common constraint now that all of our machines are ultimately working to combine all the results into a single frame. And so by breaking the frame, so we get back to the title of the talk,
we're breaking this sort of underlying assumption that is actually a big constraint in parallel graphics. We're also, by the way, very robust to load balancing issues. One of these samplers slows down, that's not going to destroy the image, it's not going to make you fall below 60 milliseconds and drop from 60 hertz to 30 hertz all of a sudden. We're very robust to that kind of thing. Of course, this is not anything like what current displays are like. That's part of why we're here. I mean, the idea of frames and pixels is baked directly into like PBI interface, having notions of frames and pixels. So this is not a good match now, but we think it might be interesting in terms of futuristic displays. And so we've been talking to Mike about LCOS and organic LED and the cool ideas that he and Gary Starkweather have for, for building tileable displays that have very large area and very fine addressable resolution. Lots of per pixel logic might be possible, lots of opportunities to do kind of smarts in the display. And that's a good idea because if you want, a printer resolution wall in your office and on your desk, you better not be trying to generate all of those pixels all the time. So this is going to be our pitch at this panel at SIGGRAPH 2005 called the Ultimate Display. You've sort of seen the punchline now. Looking forward, just to sort of wrap up, the insight that we've had after thinking about this for a little while, that the reconstruction problem that we're interested in is mostly about ignoring the wrong samples. Like the really harmful samples are the ones that are on the other side of an edge, either a spatial edge or a temporal edge. The other way of just ignoring those in standard old reconstruction would work really well. An example of this was shown in SIGGRAPH, was it last year or the year before? Gudiabala and Cornell did something, and Jack Tumlin has worked on very similar ideas called pixels, where the basic idea is if you know a priori where some of the discontinuities are going to be in your image, in this case they did silhouette finding and some discontinuity meshing kind of ideas to find the shadow and the silhouette boundaries. And when you did this sample quite sparsely, you can do reconstruction on this very sparse set of samples and get a beautiful looking image that does, but still has nice sharp edges. And so we would like to extend this kind of notion into the temporal domain. We're not sure how yet. We'd like this notion of temporal edges, or space-time edges, basically sort of sheets going through space-time. If we could find and exploit a priori knowledge, or perhaps just use some robust estimator like Jack's trilateral filtering ideas, we think that would be very powerful. We think there's lessons to be learned from video compression. There's very direct parallels between the adaptive sampling that we've done and the conditional replenishment techniques that video compression literature looked into. These days, those are somewhat out of favor compared to just motion compensation, exploiting optical flow, and that's akin to the reprojection of samples that we're doing. Now, we're trying to do synthesis, not compression, right? We're trying not to generate all the pixels and then compress them. That would go against our sort of philosophy, but I think there are lessons from the video compression literature that we could probably learn. And point-based rendering is up here. There's a whole field of point-based rendering that started with Turner Whitted. One has to be the most cited temp report in graphics many years ago. Point-based rendering these days uses much more sophisticated filters than what we do. And if we could extend those filters to have a temporal dimension, we might be able to get some really neat DVR kind of applications of this work. And furthermore, we need to make this work with fast ray tracers. Getting back to Jack's question, I mean, OpenRT goes much faster, but our implementation of it doesn't go. It's not just because we destroy the spatial coherence that they exploit. It's also because we can't use a lot of their infrastructure for shading. We have to do our own texture mapping, our own shading, all these various things. Because if we're not, but we definitely need to learn from the fast ray tracing folks. So those are our goals. We want to make this whole process fast and practical. We think that this is a good way to do very large displays. At the very least, it's an interesting approach to take. We'd like to apply these ideas to global illumination, extend these ideas to things like path tracing. That's not trivial because if you shoot two samples in the same place and they take very different paths, they might get very different colors. That's not, you don't want to confuse that for a temporal gradient, for thinking that something has changed there. So you need some way of deconflating the RDF reflectance and spatial temporal change. 3D scanning is something I'm working on. We have a laser rangefinder is a real-life ray tracer. You find in something, you tell you how far away it is. So we're building a new type of 3D scanner that's a laser rangefinder with a couple of Gal twitching mirrors that will be guided, where the laser will be guided instead of it's like an oblivious kind of raster pattern. It will actually be guided by, to go back and sample areas that seem to be changing or detecting discontinuities. We've got some really interesting conversations going on with Jack and with Mike about applying these directly to imaging devices. Could you build cameras that did this adaptive sampling and sort of so that the bandwidth coming off the chip, and pins are a limiting factor, bandwidth coming off the chip is going to be the limit soon, as opposed to the number of sensors on the chip, which is growing and growing and growing. So what if you could do adaptive sampling so that, what you took off the chip was, the same, you were sampling where it mattered. An interesting opportunity there is the opportunity to do some pre-filtering by pooling many sensors together in regions that you know you're sparsely sampling. We talked about how we'd like to build funky new display hardware. We're talking about that. And this is a nice match for people who are trying to do perceptually adaptive graphics, where you focus in on regions that you know are perceptually important. This is a very natural framework for that. And finally, we have some very half-baked ideas about doing sampling and reconstruction directly in the gradient domain. Jack has a really kind of thrilling paper about the advantages that you would get if you could build cameras that operated in the gradient domain. And maybe we can use that. For example, I have this idea that if you sample a crosshair, you shoot a few rays, and you detect that there's a gradient there, there's some change there in space, shooting more rays is virtually free and becomes more and more free as the communications computation disconnect continues. So shoot a whole bunch of rays, do a little gradient descent, literally, and try to find the edge, and then just report that. That one, throw away all the data that you collect, all those rays, and just summarize them as saying, here is the edge, and this is its orientation, and this is the gradient across it. I think that would be very powerful and allow you to get away with even fewer, maybe another order of magnitude fewer samples. That's it. Thanks so much for listening, and we'll be happy to take questions now. Thanks again. Sorry I went late. Yes?
You had this RMS measure of image quality, which I think works finely for images of machines and that like. But what happens if you put human bodies and human faces there, where people have are very sensitive to, especially mom versus not mom?
Absolutely, absolutely. Yeah, so I think that the really right way to do this is with the user study, some sort of past performance study, perhaps. That's hard, and it takes time. Ben, you're the better person to answer this.
I think that's the right answer.
But I mean, at the very least, we have played with perceptually driven, sort of perceptually motivated visual difference predictors. Mm-hmm. And like Ben said, we still win, but we look at the results of those things and where they say what they say is important and not important. We don't agree. We think that they're not designed for this kind of analysis, and so we don't think the right predictor has been designed yet. So the only thing that's left is to put humans in front of this and do studies, and so we'd like to make this fast enough that we can really do interactive studies. Mm-hmm. So that's sort of our mission statement. So even if it means taking the Utah guys and taking their supercomputers mm-hmm. and doing very, very, very fast ray tracing, even if it takes 512 processors in order to drive a system like this, then we could start to do actual interactive ray tracing. We wouldn't have to do this in simulation. So that's where we'd like to go.
Of course, human retina is not the only consumer of these pixels. I think Jack had these guys.
Who else are humans as a consumer?
Pardon?
Who else have humans these displays?
Did you talk about your art? Your art project, yeah.
Oh, yes. One big opening area here is the notion of digital archiving for museum collections. That really what we would like is to convert everything that we'd like to save about this artifact into bits. So the more you look at that, the more you realize there are a lot of it's not clear what should be recorded. How much of the appearance field should we get? What should we slice? Should we have true multispectral imaging, for example? Is that worthwhile? So anyhow, it's sort of like we're getting a hole in the wall and seeing there's this big cavern behind it. So.
Any other questions?
And one comment was when you were showing the blurring in the dynamic scenes, it reminds me a lot of when you're watching a movie, like a film, a celluloid movie, and anytime there's any sort of pan, particularly the slow pans, you get the same effect.
Right.
And it sort of leads me to think that there has to be some sort of psychophysical benchmarks for like when this effect becomes unacceptable to viewers. Like it's the kind of thing that when you know when to look for it, it's really annoying. And you don't see this on 3D graphics displays, and you don't see it on digital projectors in the film studios or film showings.
So you're talking about the motion blur, that kind of stuff.
Well, it's not
like post-motion blur.
No. I'm talking about like when next time you watch a movie, go see a movie tonight, and then like a celluloid movie, and anytime there's any sort of pan at all, you'll see blurring. And it's not because there's motion. It's not,
Yeah, there's a double flash.
right, and it's not because each frame is blurred. It's just it's a presentation artifact. But if you ask anyone, ask the person sitting next to you if they notice it. Yeah, they don't know what you're talking about.
There's an interesting, Bill Thompson at Utah had an interesting comment. He was talking about the psychophysicists who would like to and have, but can't very well study certain phenomena. Like the example is I throw a basketball at your face and you can easily catch it, no problem. That's a hard thing to study, sort of in virtual reality, if you will, right? But they just can't replicate all the phenomena that they know are there, and they think it's probably because 60 hertz isn't fast enough. Especially with double buffer graphics, where what you're really getting is up to 33 hertz, or 33 milliseconds of delay.
What's the reference? What was the reference?
Did he give us a reference?
He did.
He said he would send it to us.
Yeah.
But the guy's name is Bill Thompson at Utah, and if you want to email him, I'm sure.
He was telling us about people who were complaining to him at some conference, so it wasn't.
That was cool.
But we've gotten, just as we've gotten, it's very easy to forget the assumption about implicit in framed rendering. It's also easy to forget that we assume that the intensities should not change continuously as well. That we're essentially point sampling in intensity, and our reconstruction temporally should be a box filter, as if that pixel should not change at all between frames. So even in the frameless rendering, they're doing random updates, but the assumption is that pixel will not change until we update it, instead of any notion of a higher order fit. And I think that ties into that basketball example.
And frameless rendering that's why you brought it up, a frameless renderer should be much
and
more promising.
Human vision is wildly quirky in what we do and don't notice.
Yeah, that's very interesting. Okay, well, thanks.
Well, so of course they'll be around after this. Tea and coffee and questions.
Speaking totally from ignorance, I suspect if a human state...
What happened if